Professor Sugisaki, I think we can begin our lecture. Okay. I hereby welcome everyone for the fourth lecture of quantum chemistry and quantum computers, which is being streamed on live YouTube too. Over to you, Professor Sugisaki.
So, thank you very much for introduction, and welcome to the fourth lecture of the quantum chemistry on quantum computers. And today I'm going to talk about the Fermion Qubit transformations and quantum circuit constructions. In the previous lecture, I introduced the basic idea of quantum phase estimation for quantum circuit. This is quantum chemistry. So the basic idea of quantum phase estimation is something like that. We have a wave function. It can be a approximate one or exact one, and perform some time evolution operator. Apply a time evolution operator to the wave function. If the wave function is an eigenfunction of the Hamiltonian, it causes just a phase shift depending on the energy. So if we can determine the phase shift caused by the time evolution, we can extract the energy eigenvalue of this system. And this is the basic idea of quantum phase estimation. So in order to perform this quantum phase estimation, we have to map the wave function on the qubit. And also we have to generate a quantum circuit corresponding to this time evolution operator. So how to map the wave functions? Let's think about the wave function structure of wave function based on the shear expansion. The correlative wave function is expressed by the linear combination of theta determinant. So this is a molecular orbital of the hydrogen molecule, so a water molecule in the H2 base set, and Hagen-Fock wave function can be represented as shown here. And if we apply a shear expansion, the wave function can be something like this. The Hagen-Fock stays some one electron excited configuration and two electron excited configuration and so on. Up to, in this case, we can think about up to 4 electron excited configurations. So the wave function is basically represented by a linear combination of these theta determinants. Actually, this linear combination of theta determinant is actually the quantum superposition state. So this is the basic idea. So we can express the correlative wave function as a quantum superposition state. And the simplest wave function mapping approach is the direct mapping. In the direct mapping, each qubit stores an octation number of particular spin orbitals. So it means if there is corresponding, we need if the wave function has n of the spin orbitals, we need n of the qubits to map the wave function. And the qubit should be in the one state if the corresponding spin orbital is occupied. And if the corresponding spin orbital is unoccupied, the qubit should be in the zero state. So the wave function of the Hagen-Fock configuration can be represented like in this case, this is the 4 electron in 4 orbital cases. The wave function of the Hagen-Fock configuration can be represented just 1, 1, 1, 1, 0, 0, 0, 0. And we usually use the alpha beta alignment. And CI wave function can be represented by a quantum superposition of different computation basic states. So this theta determinant can be represented as 1101100 stage. And this state can correspond to 1110001 stage. And this becomes the 11001100 stage. And the question becomes a question of the function state. So basically, if we have n qubit where n is the number of spin orbitals, we can represent any wave function of the system, basically. Of course, we have to optimize the question, but basically we can represent any wave function. So by using this diagram mapping, the Hasse-Fock wave function can be prepared by the NE of the power X or not J, where NE is the number of electrons in the active space. So the quantum computation starts as the initial state, the state inside to the 0 state, and by applying the power X J to the molecular spin orbital, those are occupied in the Hasse-Fock basis, can generate the 1111000 states. So we need NE of the power xj to generate the Hasse-Fock state. And in order to perform the quantum chemical calculation on quantum computers, we have to map the Hamiltonian to the qubit Hamiltonian as well. So we have to transform the quantum Hamiltonian shown here, which is described as by a creation and initiation operators. And these quantum Hamiltonian should be mapped onto the qubit Hamiltonian, which consists of the strings of power operators. So if we use the diagram mapping, we can anticipate that this creation operator can be represented by this operator, where P in the subscript corresponds to the number of qubits, the qubits, P qubits. So creation operator can, if we can transform the 0 state to 1 state, it corresponds to the creation operators. And if we change the 1 state to the 0 state, it corresponds to the initiation operators. However, because the electrons are fermions, so wave function is anti-symmetric. So creation and initiation operator should satisfy these anti-communication relations. But the creation and initiation operator defined above here doesn't satisfy this anti-communication relations. Because let us think about this APAQ, AP dollar, AQ dollar, plus AQ dollar, AP dollar. If we define the creation operator as shown here, applying this creation operator to P qubit doesn't have no effect on the quantum scale of the qubit and vice versa. So if we define the creation and initiation operator as shown here, this operator doesn't satisfy this anti-communication relationship. So we have to define the creation and initiation operator so as to satisfy these anti-communication relations. In order to define the Jordan-Wigner transform, we can use the Jordan-Wigner transformation. The Jordan-Wigner transformation, the creation and initialization operators are defined as shown here. And this part is exactly the same as this part. But we need additional public key gates, public key operators from 0 to p minus 1 qubit. So let us check whether these anti-commutation initialization operators satisfy these anti-commutation relations. Let us think about if we assume that P is larger than Q, and let us calculate this first anti-commutation relation equation. And AP data is written as shown here. It's a power x I y p gate p operator and additional power c operators from 0 to p minus 1. And also AQ data can be written as shown here. So AP data AQ can be calculated as shown here. The power c gate, power c operators from 0 to q minus 1 will vanish because the power c times power c become identity operator. So C0 times C0 becomes the identity operator. So only the power c gate, power c operator between q minus 1, sorry, this is q plus 1 to c p minus 1 doesn't will remain. The difference of AP data AQ and AQ data AQ data AP data, the difference appears in the this operator acting on the Q's function in qubit. In a couple cases, we perform this operator will change the 0 state to 1 state, and then apply a power c operator. So applying this operator, if the qubit is in the 1 0 state, this operator changes the 0 state to 1 state, and then apply power c, so we can obtain the minus 1 as an eigenvalue of the power c operator. In the bottom cases, we apply a power c operator before applying this operation. So apply power c and then change the qubit from the state from 0 to 1. So if the accused qubit is in the 0 state, we can obtain plus 1 as an eigenvalue of power c, and then this operator will change from the state from 0 to 1. So in this case, the difference of the sign can come from the these terms. So in this case, so AP plus AP data plus AP data AQ data and AQ data AP data has different sign. So AP data AQ data plus AQ data AP data becomes 0. And a similar transformation can be equation can be obtained also in the initialization operators AP AQ case. So if we apply a Jordan-Wigner transformation, and let us think about the one electron operator as shown here. If we apply a Jordan-Wigner transformation to AP data and AQ, we can obtain the this function, this operators written in the parallel operators. And this operator can be expanded as shown here. As you can see, we have real operators. And also, we have imaginary operators. However, the Hamiltonian is real. So why this imaginary operator appears? So how to remove these imaginary operators? So the Hamiltonian have complex conjugate terms. If we calculate this summation AP delta AQ plus AQ delta AP, which this is the complex conjugate of AP delta AQ. Because the complex conjugate have the imaginary part has a different sign of the original one. So summing these two terms will result in only the real operators. Again, this is the one electron terms. In the Joule-Wigner transformation, the electron occupancy is stored locally. So it means that if we see the quantum state of particular qubit, we can know the occupation number of particular spin orbitals. However, in the Joule-Wigner transformation, the parity information is stored non-locally. It means we have to check the quantum state all of the p minus 1s to q plus 1 qubits to know where minus 1 should be applied or not by applying this Hamiltonian terms. So basically, if we apply a Joule-Wigner transformation, the resultant operator have order n of the Pauli field operator, where n is the number of qubits. So number of Pauli operators in the Pauli string is order n. So in this Joule-Wigner transformation, the electron occupancy is stored locally, and parity is stored non-locally. How about the trying the perform the Fermion cube mapping in order to electron occupancy will store non-locally and parity information will store locally. This is known as the parity basis. In the parity basis, the electron occupancy is stored non-locally, but parity information is stored locally. And whereas write the Fi as occupation number of spin orbitals, the transformation matrix from occupation number base to parity base is shown here. And this is the occupation number base, quantum state based on the occupation number. In other words, qubit representation in the Jordan-Wigner transformation. And this is a transform matrix. As you can see, this transformation matrix has only one term in the bottom of the triangular matrix. And the resultant quantum state can be written as shown here. This is the representation in parity base. Unfortunately, because the parity base stores the electron occupancy non-locally, the number of parity operators in the parity string become also order n. So how about in the Jordan-Wigner or parity basis, one of the electron occupancy or parity information is stored locally, and other in the non-local manner, non-local stored. So how about think about the approach? So both the electron occupancy and parity information will store non-locally. And this is known as the Bravyi Kitaev transformation. In the Bravyi Kitaev transformation, both electron occupancy and parity information are stored non-locally. Again, write Fi as the occupation number of the spin orbitals. The transformation matrix for the occupation number based Bravyi Kitaev is shown here. Again, this is the occupation number base. About the cubic representation in Wigner. If we apply this transformation, the representation of Bravyi Kitaev in Bravyi Kitaev transformation is shown here. As you can see, this F0, F2, F4, F6 correspond to the occupation number of spin alpha electrons. So spin alpha, some cubic tracks the occupation number of particular spin orbitals, but others tracks the sum of the occupation numbers. If we apply this Bravyi Kitaev transformation, the number of Paris operators in the Paris string become omega log n. So the number of Paris operators will decrease by applying Bravyi Kitaev transformation instead of the Jordan Wigner. And this transformation matrix can be generated by using this equation. Let's start from this t to the third power is this nth power corresponds to the dimension. I mean let's start to the beta 2 to the third power equal 1. Beta of the 2 to the x power can be represented as shown here. The diagram part is the matrix of the 2 to the x minus 1 power. And this part is 0. All the matrix component is 0. And this part, the bottom of the matrix is all 1 state. So beta to the beta 2 to the third power is written as shown here. As you can see, this is the first beta 1, and the bottom part is 1. This can be regarded as a beta 2. So beta 2 can be found as shown here. Again, this part is over 0, and this part, the bottom part, is 1. Again, this part will copy and paste it here. Upper right part is over 0, and so upper right part is over 0, and bottom left part is the bottom. In the bottom is 1 state, and other is 0 state. So we can construct the Bravyi Kitaev transformation matrix as shown here. So basically, we need the n of the qubits to store the wave function, where n is the number of spin orbitals. However, because let's think about the quantum chemical calculation on hydrogen molecule. The hydrogen molecule has only 2 electrons. So it means, let's think about the Jordan-Wigner cases in the SL3G base set. In the Jordan-Wigner case, in the Jordan-Wigner cases, the occupation number, each qubit represents the occupation number. So in the hydrogen molecule, in the SL3G base set, there are 2 molecular orbitals, so 4 spin orbitals, and 2 electrons. So it means only possible configuration is 1100 or 1001, 0110 or 0011 if we think about the spin single state. 111, for example, 1111 state is 4 electrons in 4 spin orbitals. So it means that it corresponds to the dianion of the hydrogen molecule. And also, let's think about the 1000 state. This corresponds to the 1 electron state. So it corresponds to the cation state of the hydrogen molecule. So the number of 1 state is always 2 in the hydrogen molecule. So in order to use this symmetry, we can reduce the number of qubits to store the wave function. And the approach is known as the compact mapping. So here, the state of the symmetric system of the qubit system are simply enumerated and equated. So it means that let's think about the shear expansion action here. We just write this state determinant corresponds to 0000 state. And this determinant to assign to 0001 state. And this state, this state determinant is assigned to 0010 state, and so on. In this case, the number of qubits required for the wave function mapping is always smaller than the direct mapping based approach, such as Wigner. However, also in this approach, only symmetric adaptive subspace can be explored. So we don't have to let us think about the quantum computer with noisy one. If we apply a Wigner transformation, and unfortunately the quantum computer is very noisy, and the big flip occurs. If big flip occurs, it will change the quantum state from 0 to 1 or 1 to 0. So it corresponds to the ionization. I mean, if the quantum state changes from 0 to 1, it means the addition 1 electron. And if the quantum state changes from 1 to 0, it corresponds to the ionization of the quantum state. So, but if we use the compact mapping, only symmetric adaptive subspace can be explored. But unfortunately, the transformation from Fermionic to qubit Hamiltonian is not straightforward. There's only a few number of applications based on the compact mapping. Only the small molecule, such as hydrogen. So these Fermion qubit transformations can be performed by using an OpenFermion, which is a Python library for simulating Fermionic systems. By using OpenFermion, we can easily generate the qubit Hamiltonian from Fermionic Hamiltonian. And OpenFermion can be downloaded from this website. And let us think about the Hamiltonian as shown here. Some constant term and 1 electron operators, as shown here. The Python program of to use the OpenFermion is something like this. First, import OpenFermion, some function from operators and conformers formations. And then in the Hamiltonian is defined as shown here. Fermion operator and the vacant appliances correspond to the term without any equation initiation operators. And in this term, this 0, 1 corresponds to apply this 1 corresponds to the creation operator. So apply creation operator to qubits, those qubits. And this term, this means that 0 in the second means the anticipation operator. So this means that apply anticipation operator to close qubit. This question is true. So this line corresponds to the definition of this term. Again, this term can be defined as shown here, applying creation operator to the one qubit. Also, they apply anticipation operator to one qubit. With question hi, h1. And this term, again, this term can be defined as shown here, applying the anticipation operator to the qubit and applying a creation operator to one qubit. With the question h1. Again, this means the applying anticipation operator to one qubit and applying a creation operator to close qubit with question h1. And this is the Hamiltonian defined in the Fermionic operator. In order to perform, for example, John Wigner transformation, it's just applying this term. I mean, the Hamiltonian in the Jordan-Wigner transformation can be generated by using this Jordan-Wigner versus the original Hamiltonian. And if we apply this Jordan-Wigner transformation, the resultant Hamiltonian is generally of course the Hamiltonian is real, but if we apply just applying this Jordan-Wigner, the resultant Hamiltonian is complex one. So in order to remove the imaginary term, we apply a complex function. Let me demonstrate that using the Fermion Qubit transformation using OpenFermion. And in this case, I will discuss the generation of S-square operator. S-square operator can be defined as shown here. SC, x plus x minus x plus divided by 2. And this function can generate the S-square operator in the where n and more is the number of molecular orbitals. So let us think about n equal 2. And S-square operator can be generated by using this S-square operator. Before applying this function, we have to import the OpenFermion and also some function from OpenFermion library. The result is shown here. This is the S-square operator in the 2 molecular orbital case. This hat means the creation operator. The number without hat is the anticipation operator. So this term corresponds to 0.25 times A0 gaga A0 A0 gaga A0 minus 0.25 A0 gaga A0 A1 gaga A1 and so on. And this is the S-square operator in the second quantized form. And we will apply a Jordan-Wigner. You can see that we can obtain the equal operator in the Jordan-Wigner base. But the question has the imaginary part because J, so to remove the this imaginary part, we can apply a complex function. As you can see, applying this complex function, we can remove the imaginary part. So in the next, we're going to generate the square operator in the Bravyi Kitaev. Just applying this Bravyi Kitaev. The result is something like this. As you can see, the number of Pauli operator will appear in the Pauli string. It's some little bit smaller in Bravyi Kitaev base. So basically, we can generate the Qubit Hamiltonian using Jordan-Wigner of Bravyi Kitaev, and so on. And let me check if the generated square operator has the exact structure. So let us think about the one molecular state, which corresponds to the Hartree-Fock configuration in the two electron in two molecular orbital bases, and then calculate the expression value of the square operator. The expression value calculation is we can be calculated by using a sparse matrix. So first, we have to define the Hartree-Fock space using episode with string. So this 12 corresponds to the decimal representation of the 1100. So this means that one times 2 to the third power plus 1 times 2 to the third plus 0 times 2 to the 1s plus 0 times 2 to the 0. The array, this, if we define the this state, the corresponding wave function is shown here. Just determine corresponding to 1100 state has the one question. Others determine has the question. So in order to perform the calculation, we have to define the square operator in the sparse operator. Because the Hamilton wave function, in this case, the wave function is defined in the Jordan-Wigner basis. So we have to generate the sparse operator in the Jordan-Wigner basis. By using this sparse operator, in the OpenFermion, there's a function in expectations. We can calculate the expectation value of the sparse operator. So this find this here we calculate the expectation value of the square operator of the Hagen-Fox wave function. The result is of course 0 because the RHS wave function is the spin single wave function. So let's think about the ROHF wave function. ROHF wave function can be represented as 101 space. So this corresponds to this one. So ROHF space is written something like this. Again, if we calculate the square value of the ROHF wave functions, the result is of course 2.0 because spin triple space. So generally we can define the if we can define the some operators in the function form, we can generate the Qubit Hamiltonian using OpenFermion, and also we can calculate the expression value of the operator by using the expectation this function. So we can generate the Qubit operators by using Jordan-Wigner or Bravyi Kitaev or something, or any other wave function mapping approach. So we have to generate the quantum circuit corresponding to time evolution operator in order to perform the quantum phase estimation. So let's think about the hydrogen molecule in the H3G basis. So the system has 4 spin orbitals in the Bravyi Kitaev transformation. The Hamiltonian becomes something like this. This is the constant time and Parity acting on the Isos Qubit and the up to 4 power operator terms. But because in the Bravyi Kitaev, the allowed configurations are only 1000 or 110, sorry, 1000 and 010. So the second and fourth qubit are always 0. So by using this symmetry, we can reduce the Hamiltonian by using only 2 qubits, using the first and third qubit. The result on the Hamiltonian is something like this. So we are thinking about the construction of the time evolution function for the time evolution operator using this Hamiltonian. The time evolution operator can be written as shown here. It means minus IHT. So H is a linear combination of these power strings. So first, we have, so this is the, of course, we can generate the matrix, space matrix corresponding to this time evolution operators. But we have, in order to construct the function, we have to, the time evolution operator should be decomposed, but in order to generate the function based on the basis function gate. So in order to perform, we generally apply a total composition. So this exponential function will decompose as a product of the exponential of the Parity operator. So here, and then in this case, in the exponential, we have only one Parity string. So we can construct easily construct the function corresponding to, for example, this term. So by applying the total composition, the time evolution operator becomes something like this. And we have to construct the function corresponding to each exponential term and then combine to generate the time evolution operators, original time evolution operators. An approach to construct the function corresponding to time evolution operator can be summarized in this paper. Anyway, so let us think about the construction of the first. Let us think about the first time. This is, in this case, the inside of the exponential is just G1 is just a question, and 1 is the identity operator, and T is just a time. So this term calls just a global phase shift. So global phase is independent on the function scale. So this term is just a constant contribution to the phase shift. So basically, we don't have to simulate this term. But if you have to simulate this term, you can use this function. This is the phase shift of phase J defined as shown here. So first perform the phase shift on this one scale, and then perform Parity X to change the one scale to 0 scale and 0 scale to 1 scale, and then perform another phase shift J, and then apply another Parity X J to recover the original state. So applying this function K, we can simulate this global phase shift. And let us think about the second term, exponential minus IGQ C0 T term. The Parity Z is defined as shown here. It is a diagonal form. So if we apply this operator to 0 state, it returns the phase exponential minus IG to T. If we apply the same operator to the 1 state, it returns exponential plus IG to T. So in order to perform this operation, actually the RCJ is very similar form of this operator as shown here. RCJ is defined as shown here. So if we this operation can be realized by applying R3 gate by setting theta over 2 equals G to T. So it means that theta equals 2 G to T. The third gate is very similar gate, but the Parity gate, Parity gate will act on the one qubit. So in this case, this operation can be realized by applying R3 gate to the Q1 with the rotation angle theta equal to G3T. And next, let's think about this term. In this term, there are two Parity operators. So this Parity 0, Parity 1 can be written as shown here. This is just a direct product of the Parity 0 and Parity 1. So if we apply this operator to zero state, it returns the phase exponential minus I G for T. Also, if we apply this operator to the 1-1 state, again, the exponential minus IG for T, the phase can be obtained. And if we apply this operator to 1-0-1 state or 1-0 state, it returns the phase exponential plus IG for T. So, generally, if the exponential term has several Parity operators, in that case, apply a phase shift exponential minus IGT if the number of qubits in the one state is even. If the number of qubits in the one state is odd, in that case, we apply a phase shift exponential plus IG4T. And this operation can be performed by using a single gate to correct the number of qubits in the one state. Let us apply a single gate to this case. That if the number of qubits in the one state is even, the resultant from the state, the second qubit of the resultant from the state is over 0. And if the number of qubits in the one state is odd, the quantum state after the signal operation, the second qubit is always one state. So the second qubit is 0. In the case of second qubit is 0, we apply exponential minus IG4T. And second qubit is one state, we apply exponential plus IG4T phase. So this operation can be realized by applying single gate to correct the number of qubits in the one state to this Q1, and then apply a RC gate to perform the phase shift. We need additional single gate to recover the original state. The next is this term. This term has two Parity X gates. In this case, first, we apply a Agamal gate to transform from X basis to Z base, and then perform the quantum study corresponding to minus exponential minus IG5 to C0, C1, T terms, as shown here. And then apply reverse transformation from Z basis to X basis by applying another Agamal gate. So this term can be simulated by using this quantum study. In the case of the Parity Y operators that we again transform the Y basis to Z basis by applying Rxj with the rotation angle theta equal pi over 2. And then apply the exponential minus IG6 terms. And finally, apply reverse transformation from Y. So this is incorrect. Reverse transformation from Z basis to Y basis by applying additional Rxj with a rotation angle minus pi over 2. So general procedure of the construction for the time evolution operator can be summarized as here. We can think about the exponential minus IG x0 g1 x2 y5 g6 y7 t as an example. First, we apply gamma j to the qubit so power x will act. In this case, the zeros and shrunk qubit. And then apply Rx with the rotation of pi over 2 to the qubit so Parity Y will act. And then perform the signal operations. Connect the all qubits so pi operator will act by a single wire. This operation, this single gate will correct the number 1 state in function of the number 1 state in the Q7. And then perform the RCJ to the bottom qubit. And then perform the another single wire in the reverse order to all qubits so pi operator will act by a single operator. And then perform the Rx minus pi over 2 gate to qubit. So Parity, sorry, is this Parity, not Parity, but Parity Y will act. Applying another gamma gate to the qubit, so Parity X will act. But in the quantum phase estimation, we have to simulate the control time evolution operator. Okay, so we have to generate the time evolution quantum circuit corresponding control time evolution operators, like this. And this is an example of the time evolution operators, quantum circuit corresponding to time evolution operators. In order to perform control time evolution operator, only we have to do is replace this RCJ to the control RCJ, where the control qubit is the ancillary qubit in the top qubit in the this quantum circuit. In this case, if we remove this RCJ, the applying signal twice will generate the original state. So, and Rx minus Rx will generate the original state. Applying gamma twice generates the original state. So, if we don't, if this RCJ is removed, it corresponds to the identity operator. So, a control time evolution operator means that apply a time evolution operator if and only if the ancillary qubit is in the 1 state. So, if the ancillary qubit is the 1 state, apply this just original control time evolution operator. And apply nothing if the control qubit is in the 0 state. So if the ancillary qubit is in the first stage, it corresponds to the removal of this RCJ. So if we remove this RCJ, the resultant from the circuit becomes identity operator. So we can simulate the control time evolution operator by using this kind of quantum circuit. And also the signal, let's say something about the signal brother. The quantum circuit for the time evolution operator has a form of something like this, the signal brother, and RC and reverse signal brother. But this quantum circuit is equivalent to this quantum circuit. But usually the quantum circuit depicted in A is used because in this quantum circuit is equivalent to the A, but in this quantum circuit, we have to apply a signal gate, with non-nearest neighbor qubits. Especially in the NIST devices, sometimes the application of signal gate is very limited. Sometimes only the nearest neighbor qubit can be signal gate can be applied only the nearest neighbor qubits. So this quantum circuit is equivalent, but generally we use this quantum circuit. So the time is almost over. So I will give you an exercise problem. We are thinking about we have a quantum qubit Hamiltonian of the form of the Hamiltonian is 0.5 x0 x1 plus 0.5 times y0 y1. So please construct the quantum circuit on IBM Q for the time evolution operator with t equal pi. So this time evolution operator can be written by applying a Jordan-Wigner transformation. By applying a Jordan-Wigner target composition, this time evolution operator can be decomposed by exponential minus 0.5i x0 x1 t times exponential minus 0.5 I y0 y1 t. So please construct the quantum circuit on the IMQ with the time evolution operator with t equal pi. And then please simulate the time evolution quantum circuit with the following condition. So start from the 1st stage by applying an xk, Parity xk before the time evolution circuit and measure qubit after the time evolution. Also set the evolution time t equal pi over 4, pi over 2, 3 pi over 4, and pi. And run the quantum circuit on IBM Q with a state vector simulator and check the measurement outcome. And how the measurement outcome will change by changing the evolution time. And also please check the quantum circuit simulation using IBM Q machine, not simulator, but a real machine, and check the measurement outcome. And how the measurement outcome will change, and also how the errors arises by comparing the result from the real quantum computers and the result from the state vector simulator. I will give you some results in the next lecture, in the beginning of the lecture. So this is the end of today's talk. I'm very happy to accept your questions. Thank you very much.
Thank you for your excellent talk, Professor Sugisaki. I request the Zoom participants to ask questions, if any. In the meantime, I'll also check the YouTube screen. Seems like there are no questions as of now. Maybe we'll wait for a couple of minutes, then we'll close the lecture. Is that okay, Professor? Since there are no questions,